Good morning, everyone. I'm Vlad Shalaev from Purdue University. Well, it's my pleasure to welcome you to this very first plenary session of this meta conference. And our first speaker is Professor Demetrios Christodoulides from University of Central Florida. He has lots of first discoveries, truly pioneering results, ranging from all type of solitones, including incoherent solitones, to accelerating beams, and to PT symmetry optics, and that's, I believe, the subject of his presentation today. He, of course, was awarded many times for his wonderful work, including the Wood Prize from the Optical Society of America. Please join me in welcoming Prof. Demetrios.
Thank you, Vlad. Good morning, everyone. Again, my name is Demetrios Christodoulides. I'm from the College of Optics and Photonics. And as you can tell from the title, today I will be providing an overview of our activities in the general area of non-Hermitian photonics, and in particular PT symmetry. I would like to thank, of course, the organizing committees for inviting me to this beautiful event. And having said that, I will move on to my talk. Perhaps it's best to really put all these efforts within the perspective of recent developments in terms of new structures and materials. As you all know, in the early 90s, we have seen the emergence of photonic crystals. These are structures that use really high contrast in order to really, these are periodic structures that use high contrast in order to really induce gaps and, of course, allow bands. And, of course, their cousins, the photonic crystal fibers, are, of course, ever present in our technology. They are used extensively in linear fiber optics, and, of course, they're the workhorse for supercontinuum generation. Following the 90s, of course, we have seen the emergence of negative index materials, and of course, plasmonics for that matter. So if you would like to, for example, overview these activities, of course, it's best to really see them in these quadrants, in the quadrants that really involve the permittivity and permeability. So clearly, when we're dealing with this particular quadrant, where the two quantities are positives, these are normal materials such as silicon, polymers, glass, and so on and so forth. If by any chance really we venture over here where the permittivity is negative, clearly we enter the plasmonic region. And of course, in this particular quadrant where epsilon and mu is negative, of course, we're dealing with negative index materials. You may also consider this particular quadrant, and of course, we have all sort of other developments in terms of new structures, such as the ENZ. This is structures, materials that Nadir and Geda will be presenting very soon. So, a few years ago, parallel to these activities, we also wondered the following. Is there anything, we decided really to explore what one may obtain if instead of really changing the permittivity and permeability, keep the permeability as God intended, but instead, deploy gain and loss. In other words, keep the real part of the permittivity as supposed to be, but use a strong contrast between gain and loss. So the issue that I would like to ask at this point is there anything we can get if we get this synergy between index, gain, and loss in appropriate proportions? So whenever we design a structure, of course, we always rely on this basic diagram, or this triangle of basic ingredients. First and foremost, of course, is index. Every time you make a waveguide, every time you make a cavity, you have to really use the index contrast. It has been the workhorse of optics. And of course, if you want to rely on the imaginary components of the permittivity or index, of course, on this side is gain. Gain, optical amplification, is clearly a valuable commodity. You always use it to mitigate losses, to boost the optical signal, to induce nonlinear effects, and so on and so forth. On the other hand, loss, it's abundant in nature. You don't have to do anything really to bring loss. But for all practical purposes, we in the optics community, we do our very best to stay away from it. In fact, we consider loss to be a foe. So whenever we design a system, it is no surprise that most of the efforts actually move around this ridge, anywhere between index and gain. And we typically overlook this side, right, of the triangle for all good purposes, because the first reaction for anyone working in optics is to stay away from losses. But this is really justified. So, well, what we would like to ask at this point is loss always a foe? Is loss always a problem? Well, the answer is not necessarily. Let's take, for example, 3 cavities over here. One involving gain, while the other 3 happen to be lossy. Well, intuitively, one may expect that as you increase the level of loss on the nearby cavities, that the system actually, the performance of the system will degrade. This is not always true. It so happens there are many, many occasions that as we increase actually the losses, the performance of this arrangement actually gets better. So, and not only that, we may lower the losses and it gets worse. Why this is the case? So why really the system behaves like that? Well, part of the issue is because we cannot always fathom where the roots of the characteristic equation, the complex roots of the characteristic equation will actually end up on the complex plane. It may be actually something quite involved. And because of that, it's very difficult sometimes to tell what is best when it comes to these issues that involves gain and loss. So clearly, we have to use gain in a strategic fashion, and especially in issues in areas like metamaterials. On occasions, metamaterials exploit metals. And of course, losses are inherent to the system. So how do we introduce gain in such systems, including nanolasers, phasers, plasmonics, or coaxial nanolasers that I'm showing over here? You have to do it in a strategic way. You cannot just sprinkle loss all over the place. If you just do that, you don't know if really the mode you would like to will laze, or some other parasitic modes are actually going to get activated. So at the end of the day, you have to really use it in a clever way if you like to really engage the mode you have in mind. So how do you do that? Well, part of the answer comes from an interesting place, and in particular from quantum field theories. Back in the late 90s, Carl Bender and colleagues asked the following interesting question. Should a Hamiltonian be Hermitian in order to exhibit real eigenvalues? Anyone who got, of course, an introductory course in quantum mechanics would say yes. Typically, we associate real eigenvalue spectra to Hermitian operators. But surprisingly, and this is what they found, there is a large class of Hamiltonians that by no means are Hermitian. They are not Hermitian. But even then, they exhibit entirely real spectra. This type of Hamiltonians are better known out there as parity time symmetric Hamiltonians. These are Hamiltonians that actually commute with the parity time operator. So what do we mean by this? Well, As I said before, the Hamiltonian must commute with the antilinear parity time operator. What the parity operator does, of course, flips the position, and in doing so, of course, it flips the momentum, whereas the time operator really causes a conjugate reversal. So one can show, of course, by deploying operator algebra, that if a Hamiltonian really commutes with a parity operator, then a necessary but not yet sufficient condition will be that the potential over here should respect this particular relation. In other words, V star of x, the conjugate of the complex potential in this case, should be equal to the potential with the coordinate here reflected. If you take it one step further, you will find out that the real part of this potential must be even, while the imaginary part must be antisymmetric, must be odd. So if you guarantee this relation over here, you have at least a good start. Nobody says that the spectrum will be real, but there is a good chance that the spectrum indeed will be so. So if indeed we respect parity time symmetry, then this complex parity time potential below threshold will exhibit entirely real eigenvalues everywhere in the spectrum. So to give you an example, so parity time, interestingly enough, comes with its own algebra. You have to totally redefine the concept of the bra. So for any ket, you have to really come up with an entirely new bra. And as a result, the inner products have to be redefined. So if you're dealing with quantum mechanics in general, like this one over here, right? The inner product, of course, all you have to do is take the conjugate of any eigenfunction. Of course, you're going to find out that the eigenfunctions so happen to be orthogonal. If parity time symmetry is obeyed instead, you see here in the bra, you see you have to really reflect the coordinate. As opposed to have the probability conserved, which is the case in quantum mechanics, if you impose parity time symmetry, the anti-probability is conserved. So all these peculiarities are actually a byproduct of this parity time symmetry. So let's consider a simple example. Let's consider the potential Ix raised to some power n. It takes only a few minutes to show that this potential is really parity time symmetric. In other words, it obeys the simple relation we just presented before. So if by any chance n is 2, all you get, of course, is your familiar parabolic potential that characterizes your quantum harmonic oscillator. What are the eigenfunctions over here? The eigenfunctions, of course, are the Gauss-Hermite polynomials, nicely spaced over here, right? Equally spaced. This is something you know all along from quantum mechanics. Let's say now n is 3. Even if n is 3, this is parity time symmetric, and it so happens the potential happens to be Ix cubed. Notice that it's purely imaginary in this case, and as opposed to this potential that happens to have a minimum, of course you expect that all the states will be bound. X cubed has no minimum. X cubed actually has no minimum whatsoever. However, if you analyze this potential, you're going to find, to your surprise, that all the eigenfunctions so happen to be bound, very much so, like the potential over here. All the eigenvalues are real, in spite of the fact that we have a purely imaginary potential. The only difference is that the minima of the eigenfunctions tend to evaporate, and even more importantly, the eigenfunctions are no longer orthogonal. All the eigenfunctions so happen to be skewed with respect to each other. This is very, very characteristic of no-Hermitian systems. So a few years ago, we said, well, maybe we can actually observe pretty symmetry in optics. Well, there's no way we can observe it in quantum mechanics. After all said and done, quantum mechanics is a Hermitian construction, but there's nothing that really prohibits anyone really from observing parity time symmetry in optics. So perhaps the simplest structure would be a waveguide, an even waveguide, impregnated with an equal amount of gain and loss. So if by any chance, say, this waveguide contains an equal amount of gain and loss, then parity time symmetry can be established. And the spectrum would be real. not only should be real for the bound states, it should be also real for all the radiation modes. Of course, one may say, well, what's the big deal? If you put half gain, half loss, of course, this should happen. But this is not as innocent as it looks. In reality, the reason that neutrality is actually observed over here is because you have introduced this gain-loss dipole. And as a result, there is constant flow of energy between gain and loss. So in doing so, this wind of energy introduces some interesting ramifications. So let me consider, for example, a pretty symmetric waveguide terminating in air. So before I do that, let me consider, of course, the case where this is a normal waveguide, it's a passive waveguide terminating in air. Of course, the diffraction in air will be symmetric, as you see. But if instead I replace the lossless waveguide with a parity time symmetric waveguide, because of this energy flow that always occurs, then you will find very soon that the wavefronts over here is supposed to be normal, right? In this particular case here, the wavefronts are normal. In the pretty symmetric case, they are tilted. And why they are tilted? Because the eigenfunctions, again, are skewed. As a result, at the output, energy tends to flow towards the right, where the energy flow really in accord with the energy wind between gain and loss in this particular dipole. So even though the system is by no means birefringent, this gain-loss contrast over here create this interesting process over here that is forcing really the energy to go in a certain direction. So let's say, for example, I would like to traverse this pretty symmetric waveguide over here. If I'm going to excite it, I have to go at an angle. After all said and done, this is what is going to guarantee the phase matching to this waveguide. So if I go at an angle, of course, I will go up. And then, of course, I will exit at an angle. If I would try to come back, you understand something will happen. You see, as I was going up, my gain was on my left. The loss was on my right. As I'm coming down, I will see the other way around. So as a result, if I try to come back, it will never be possible. In other words, the gain-loss dipole actually broke the reciprocity. The only way I can make it back this way will be, as opposed to come from this side, come from here, as shown in this figure. So once you introduce these dipoles, these strong dipoles of gain and loss, light can distinguish left from right. It's to some extent not reciprocal. Not, of course, a la Faraday, but it's not reciprocal for that matter. Central to this discussion is the presence of exceptional points. This is very characteristic in all non-Hermitian systems and, of course, in pretty symmetric systems. So what is an exceptional point? Well, to understand this, perhaps it's best to really look at the easy or the most trivial system of all, a two-level pretty system. This can be, say, two cavities exchanging energy in time, one exhibiting gain, the other one loss, or maybe two waveguides coupled with, because of their proximity. If by any chance you would like to really write the evolution equations, of course they take this simple form. Kappa represents the coupling, G plus G minus G represent the gain-loss contrast between these two cavities or waveguides. Well, if you want to see what's going on over here, as opposed to really, the state of the system is supposed to really move on a sphere. It looks on this hyperboloid in some funny, say, trajectories. And it's best understood if you consider, say, the eigenvectors of this system. So it's a 2 by 2 system. Of course, it has two eigenvectors. If the system was Hermitian, in other words, if G was 0, right, these eigenvectors will be 1, 1, 1 minus 1, and of course will be orthogonal. In this particular case, because I've introduced gain, you see a phase appears over here on both eigenvectors because of this interplay between coupling and gain and loss. So something interesting happens, however, so theta keeps increasing from 0 to pi over 2, depending really on the gain-loss contrast. And at pi over 2, look what happens to the eigenvectors. This will be 1, and this will be just I. And the same goes with this one, 1I. So what happens at this exceptional point, we say, at the point where theta is pi over 2, or the eigenvalue happens to be 0, is that the system loses dimensionality. It used to have two eigenvectors. At that point, the eigenvalues coalesce, and at the same time, the two eigenvectors. This is a very dramatic event, by the way. So as a result of this losing dimensionality, right, once you really cross over, then the eigenvalues start to become imaginary, purely imaginary. So depending where G, the contrast of gain loss, is with respect to the coupling, there are a certain possibilities. If G is 0, of course, we have two orthogonal eigenvectors, as you expect from the Hermitian case. As you increase really the gain loss contrast, you see the eigenvectors become skewed. Eventually, they coincide, right, at the exceptional point. And once you exceed that the exceptional point, again, they depart. So this is what we call the broken Petit phase. This is where the eigenvalues are complex. Below that, all the eigenvalues happen to be real. So all this now is characterized by this strong bifurcation. As I said, before the exceptional points, the spectrum is entirely real. Once you cross it over, you see you get the complex conjugate pairs signaling the fact that we've broken the Petit symmetry and the system now is ready to either lace or absorb. Is this only true for discrete systems? The answer is no. I mean, you may have continuous, potential distributions where exactly this happens. Say, for example, I have a waveguide over here that contains equal amounts of gain and loss, and then I keep increasing the gain-loss contrast over here. Up to a certain point, the spectrum will be entirely real. It will be real not only for the bound states, but also for the radiation modes outside the system. But if I overdo it, in other words, if the gain-loss contrast exceeds a certain critical value, right, then what happens over here, the spectrum starts to bifurcate, and one mode will experience gain, and the other one an equal amount of loss. This is what we call a symmetry breaking point. This is a phase transition point at the exceptional point where we signify the transition from real eigenvalues to complex. To some extent, in the language of optics, this can be understood as a competition between index guiding and gain guiding. Okay, so these are one of the first observations really we have in terms of these transitions. So what we did over here back in 2009, we have a coupler, a simple coupled system. It's passive, and on top of this arm, we deposit chromium. Why do we do chromium? It's just to introduce losses. Chromium was very intentionally selected because at 1.55, if you see at 1.55 microns, if you see the permittivity is purely imaginary. So all it does is just dumps a lot of losses on this arm without really perturbing, through chronic conditions, the detuning. So as we increase the chromium over here, of course, the loss increases drastically. So intuitively, if we put light in this system, one expects that as we increase the loss through depositing chromium, at the end of the day, nothing will come out. And indeed, this is the case. As we increase the chromium, as we increase the losses, exponentially the transmission disappears. But then something interesting happens. As opposed to really make the transmission less and less, the more chromium we put, the more the transmission starts to increase. So this is totally counterintuitive. How come the more, how come the more loss I put to the system, the transmission increases? And the answer has to do with that exceptional point I just told you. The system thinks that it's now time to break the symmetry, and it goes into the complex eigenvector, and as a result, transparency is reestablished. And this is not because of detuning. This is purely because of loss, because of the loss in this particular system. We obtain similar results even when we introduce gain in this particular arrangement. Gain was facilitated through two-wave mixing, lithium niobate. Again, we got exactly what we expected from this Petit symmetric system. So the next issue is, what gain and loss will actually do, say, in a periodic arrangement? So let's consider, for example, periodic structures. Well, a lot of you are familiar with photonic crystals, of course, and also periodic structures. So clearly, whenever you have periodicity, the Fogel-Bloch theorem is at play. Under Hermitian conditions, of course, we see the emergence of bands, band gaps, and so on and so forth. And of course, the orthogonality relationship between modes and bands is observed. So what will happen, for example, if I start incorporating gain and loss in every side over here in a symmetric fashion? So if I do that, so let me take, for example, this potential here. You see, these are waveguides, impregnated halfway between gain and loss, each one of them. So as I increase really the strength of the gain loss, something interesting starts to happen. The two bands, you see, the two bands in red, starts to really attract, start to really approach each other, and at the exceptional point, they make contact. So because of the gain loss, the band gap starts to close, and if you overdo it, if you keep exceeding really this magic number over here, then this is what happens to the two bands. The two bands form an oval. This is after the two bands collide, where all the eigenvalues so happen to be real. And at the same time, they have these two abrupt lines over here, these two membranes, where the spectrum happens to be complex. As a matter of fact, the eigenvalues so happen to be conjugate to each other. And at the same time, you see very well that despite of the fact that band structure is even, the eigenfunctions are all skewed again. So, of course, because of these gain-loss dipoles you have incorporated in this periodic structure, you can see all sort of interesting effect. Double refraction, in spite of the fact that everything is isotropic. You can see power oscillations because of the very fact that all the eigenfunctions happen to be skewed. The orthogonality is no longer observed. And of course, if you extend these results to 2D, you see very soon that in 2D, for example, the two bands, after they collide, they form this interesting surface over here. It's like a Chinese cookie, where on the inner surface, all the eigenvalues are real, and on these membranes, it so happens to be complex. Interestingly enough, this funny surface that results from the collision of the two bands was observed recently by Soljasic's Joanopoulos group from MIT. They use a particular, say, crystal where you have a cone over here, very similar to that of encountering graphene, where at the end of the day, after the collision of the two bands, you get really this membrane. It's a very interesting observation for that matter. So what happens, let's say, for example, what happens to a grading? Let's say I have a grading, and everyone is familiar with a grading. If it's passive, close to the band gap, close to the Bragg frequency, we have the band gap, where the transmission, of course, is zero, and of course, everything is reflected. This is standard, curves, reflection transmission curves from any grading. So the question now you have to ask is, how about if I start incorporating gain and loss in every period, and I keep increasing really this contrast of gain and loss? So what happens is the following. The band gap starts to close as I start increasing really the gain, whereas the reflectivity starts to decrease. And then there is going to be a magic contrast at the exceptional point where the entire transmission becomes 1 and the reflection goes to 0. Not only the transmission in this case is unity and the reflection is 0, but also the phase that is actually given, imparted to the wave, so happens to be 0. In other words, from this side, the grading is totally invisible to radiation. In other words, the presence of the grading has been totally erased for that matter. So the question now we have to ask is, what will happen if I come from this side? Will I see the same effect? And the answer is no. If I come from this side, then the transmission looks like that, and as I keep increasing the gain-loss contrast, the reflection, instead of diminishing, keeps increasing, and then exactly at the exceptional point, the transmission becomes unity, and the reflection starts to now exceed 100. So from this side, the grading is invisible, or from the other side, it's totally visible. So why this is the case? Well, what you did over here is you spoiled the symmetry. In other words, remember when you came from this side, you enter the grading on the gain. It goes like gain, loss, gain, loss, gain, loss. If you go from the other side, it goes loss, gain, loss, gain. And this has a totally different effect to the properties, to the optical properties of the grading itself. So this is the first experimental observation of this effect. It was done with our collaborators from Max Planck and Lange, published in 2012. This is a periodic structure. It's a mesh lattice where you see, for example, the merging of the two bands at the exceptional point. This is your exceptional point. If you exceed the exceptional point, you have this, this merging of the bands. And then if you come from this side, you see, on this side, the structure is entirely invisible. Everything goes through, no reflection whatsoever. On the other hand, if you come from the right, it's entirely visible. So this is a proof really of what you expect really to see from such a system. The same effect was observed later on by Zhang's group. This is few inches wafer. You can tell really the difference performance, the way they perform differently from either forward or backward direction. And in terms of silicon, this is a microstructure made by Sherritt's group in Caltech, featured on the cover of Nature Materials back in 2013, that pretty much demonstrates exactly the same effect. The same principle was used quite recently in demonstrating for the first time parity time synthetic laser. Pretty much what you have is a ring laser over here, and pi over 2, you incorporate a pi over 2 PT grading because of the chromium germanium involved, and you can see a single mode operation because of this breaking in the parity time symmetry regime. One interesting ramification is the possibility of optical solitons in such lattices. This is something we speculated back in 2008, and the way this works, of course, is because of this interplay of gain and loss. Why this is interesting is because typically in non-conservative systems, solitons are actually constrained, as opposed to conservative arrangements where solitons actually form lines, because at the end of the day, these nonlinear creatures tend to really serve only two masters, nonlinearity and dispersion. In dissipative systems, they form points because they have to balance also gain and loss. But it so happens that in PT-symmetric arrangements, this is totally lifted. And as a result, the system behaves almost like Hermitian, like conservative, in spite of the fact that it's by no means conservative. And as a result, you can beautifully see the formation of these entities in spite of the heavy losses and gain involved in the lattices. So another system of interest will be PT-symmetric cavities. And this is, and in particular in relation to micro-ring lasers. This work is done, the work I will be presenting here comes from Professor Gajavika's group. She will be providing more details to this on Thursday. So pretty much everyone is familiar with micro-ring resonators. They are, of course, very attractive for all sorts of applications. They have high Qs, strong confinements, small footprint, and so on and so forth. They are very good, they are ideal components for a number of applications, but it's always nice to see them, right, for laser applications. Now, the problem with lasing, of course, have them lasing, it has to do with the broad bandwidth they support. These are indium phosphide has a very broad gain. As a result, whenever you pump them, you see a series of lines. So what can you do really to make them single-moded in that respect? Well, there is several solutions over here. You can actually modify the pumps, right? You can actually incorporate the Vernier effects, DFP arrangements, and so on and so forth. But is there any way really we can actually make them lace without a lot of effort? So clearly, if you have only one cavity, you may see a number of lines emerging as long as they're above the loss line. So And typically, if you keep the loss line over here, you may see, for example, in this particular case, three lazy modes. So the question we asked some time ago is what will happen if we pair it with another cavity? Clearly, if we have gain and gain, we're going to see doublets, as you expect. But how about if we use loss instead of gain in this particular cavity over here? In other words, how about if we enforce PT symmetry? So in that case, one can show that in doing so, you totally remove all the parasitic modes, and not only that, you are totally enhancing really the mode you would like to really see. And this comes really with an enhancement factor. You see the square root. The square root that comes at the exceptional point is the one that actually provides this enhancement factor for the gain and makes this a winner. And in doing so, of course, removing the parasitic really resonances over here. So this shows, this is an SM photograph of the rings showed, used in the experiment, and these are the results. A single ring, of course, has several longitudinal modes. If you pair them together, you see the doublets, and as shown by Professor Jaffinger's group, once you pair them really with loss, everything is removed. All the dirt is removed and allows only one mode really to win. So this is pretty simple for that matter. And interestingly enough, in spite of the fact that you are using loss in the parasitic cavity, the system actually behaves better from a single ring. This is shown here in the line-like curves. And even more importantly, if you compare the single ring with the PT symmetric ring, this is the PT symmetric ring, this is a single ring, the curve, the line-like curve is free of kinks. And the reason is all the intensity now is delivered to the desired mode. The rest of the modes have been entirely suppressed. The same goes with, say, other father rings that support a series of, say, transverse modes. Not only removes all the extra transverse modes, but it also keeps the longitudinal mode of interest. So in essence, putting weight is not always a bad thing. Loss, like the counterweight that people use for their boats, can also be extremely useful in this respect. Similarly, touch-stage lasers have been demonstrated, also exploiting, say, the presence of exceptional points. And other groups, like Young's group from Washington University, have shown these beautiful bifurcations, the square root bifurcations. And of course, Mick Shaw's group has shown no reciprocal behavior in nonlinear coupled microcavities that obey PT symmetry. One of the interesting ramifications of these exceptional points, of course, is this square root behavior. So it so happens that if you position a system at this particular point, the system happens to be very sensitive to perturbations. And as a result, it holds great promise for sensing applications. This is something that was predicted by Versik's group. And there are other contributions from Elganani's group in terms of enhancing the sensitivity of these systems. An issue of interest for us is to use these no-Hermitian arrangements for optical isolators and circulators. There is no need here to really tell you why these are very useful components. Typically, if it comes to fiber optic systems, optical isolators are implemented using garnets with very strong vertex coefficients. Of course, of interest will be to have isolators on chip, and especially all dielectric chips. Well, many groups like Muzimoto, for example, is incorporating garnets on 3.5s. Of course, this is wafer bonding. It's a 7-step wafer bonding that happens to be rather cumbersome. And of course, there are many other possibilities in incorporating really the garnets directly in either silicon or other materials. Of course, always at the expense of something, maybe at the expense of bandwidth, at the expense of footprint, and so on and so forth. So the question, of course, we'd like to ask is, are magneto-optic approaches necessary for optical isolation? The answer is no. starting from Dick Smith's work from Bell Labs, and of course, culminating with the work of Lipson and Fan that was presented in PRL using silicon. So what we'd like to do over here is to see whether we can use, say, no hermeticity in order to really achieve isolation. So if we would like to do that, and especially on 3-5s, such structures, whether isolates or circulars, must be compact. They better have broad bandwidth, retain the color of the signal, be polarization sensitive, and of course, it would be nice if they use processes that are indigenous to the wafer itself. Well, it so happens that if you use gain loss contrast and nonlinearity, then you can introduce isolation. So anytime the power in the system is forced to follow a nonlinear roller coaster, the system is not reciprocal. So how can we do that on semiconductors? Well, on 3-5s, 3-5s are known for their they are very large nonlinearities. They have nonlinearities that are 9 orders more than silica glass. They come from exciton, band filling effects, and so on. The only problem, and of course they are not from the 80s, the only problem is they are heavily lossy. So in this case, we say, well, okay, if they're lossy, bring the losses in. Maybe we can use them for something useful for that time, for this, in this instance. So what we do is the following. We force the signal really to go through a successive region of gain and loss. So here is a semiconductor optical amplifier. This is a very lossy coupler. And in doing so, we can actually show that you can implement an optical circulator. A circulator is supposed to really send signals sequentially among ports from 1 to 2, from 2 to 3, 3 to 4. So the way it's done is through this sequence of gain-loss regions. You see, this hops over, right, after an amplifier. And in essence, this can be done, all these regions can be incorporated on 3-5 by selectively engineering the bandgap in these systems. So this is done really using silicon oxide, silicon nitride caps, silicon-rich nitride, in order to really write the SOA regions and the couplers. And this is how the system looks. This is a circulator, actually, that employs this sequence of gain, loss, and nonlinearity. And once you activate really the semiconductor optical amplifiers that are necessary really to produce this effect, and it's shown over here, then what is nice about, you find out that this system operates in any respect like an optical circulator with a degree of isolation of 23 dBs. Even more importantly, if you see, for example, the bandwidth over here is 20 nanometers, and all this because of this interplay between gain and loss. So what is the outlook? Well, how can you use no hermeticity? How can you use, say, PT symmetry? There is quite a bit of effort these days to introduce no hermeticity in topological insulators. This is work that is done these days by Sergeyev's group at Technion. There's quite a bit in metrology. This is from Hajavinha's group and Lanyan's group. How you use no hermeticity at especially exceptional points so as to enhance sensitivities. Metamaterials and several groups are actually involved in this effort, including Geta's group. Interestingly, some of these ideas have migrated in other areas like acoustics from Alu's group and Zhang's group. Plasmonics is going to be a good ground, especially given the fact that gain has to be judiciously introduced in these systems. Optomechanics, there's quite a bit of work done by Frank Honori and Ozdemir from University of Washington. And we have seen for the first time parity time symmetry in atomic lattices. This is work from Ming Xiao's group from China, University of Arkansas, where an entire PT lattice has been imprinted on rubidium cells. And of course, there is always the option to bring these interesting concepts in nonlinear optics. This is work by Elganainis and Konotop's group. And of course, in conjunction with other concepts, like, for example, supersymmetry and so on and so forth. So before I close my talk, I would like to say that still the interplay between gain and loss is still an open issue. It's not well understood. And it will pay off, especially to the community over here, if this synergy is actually exploited. For example, plasmonics is always an area where gain is needed. If you would like to use gain again, you have to use it in a clever fashion. And the best way to do it is to really pacify the spectrum. Provide a reference frame from where you can actually build up the gain. Otherwise, what you will see will be modes really emerging that have nothing to do really with the mode you would like to really see. So all this is actually useful in this particular respect. There are going to be, for those who would like to know more about these issues, there are going to be other sessions this coming Wednesday and Thursday dedicated to non-Hermitian photonics and PT symmetry. And with that, I would like to thank you all so much. Thank you.
Well, thanks a lot for this fantastic talk. I guess we could take one or a couple questions. Do you have any questions? Well, I see Shaya there.
Very nice talk. Enjoyed it very much. Had one sort of question, comment. In practical systems, we concern usually with insertion loss. Is that an issue in this wonderful physics?
The question is whether we should be concerned with insertion losses. And the answer is, as long as we have gain, we can always overcome insertion losses. Actually, the biggest problem we have is not so much insertion losses. It is really how we balance the gain and loss without really embottling really the Kramers-Kronig relations. That's absolutely true.
All right. Maybe we then thank again Dimitri for this great talk.
Thank you.